Thank you.
Okay, so now Luca is going to talk about the constraining HWW and HZZ with anomalous coupling with the quantum tomography.
So hello, everybody, and sorry for the overlap with the previous talk. This is going to be more fin-oriented a bit. So my background is in models of new physics in general. So as soon as I started to learn about entanglement and Bell inequalities, my attitude was like, okay, can we use these things to probe possible physics beyond the standard model? So just to clarify the problem, the purpose of the game is the following. So we consider modifications to the Higgs vector boson vertices from the standard model form, right? So here is the standard model part that we all know and love. We have the Higgs, the W boson, the Z boson, and then there is new part which could be given by some new physics, no? And then this part involves the field strengths for the W and Z boson and their duals, which are obtained with the contraction through the Levi-Civita. These couplings is what I will use to parameterize the effects of new physics. And then the purpose of the game is to see if we can tell something about those couplings. If you use this Lagrangian, you get an effective vertex of this shape, where you have the standard model part. And then here you have the new interesting parts, where you have, this is the Levi-Civita symbols. I didn't bother writing out the indices, but the saturation are in order. And this is just the shorthands for the polarization tensor vectors. I would pay particular attention to this coupling, the tilde couplings, because if they were non-zero, they would signal the presence of a CP odd part in the pseudoscalar component, basically in the Higgs boson. So the question is, can we use quantum tomography to constrain this coupling? And the answer is obviously yes, because otherwise my talk would be over here. So now we've learned about quantum tomography. You have to do measurement to reconstruct the density matrix. So I thought I would call this part theoretical quantum tomography, just to show you how I compute this from the amplitude of the processes. So in theory, we can compute things, right? So we start with an amplitude, and this is like the amplitude for the production of a massive boson that they call V. It will be a W or Z, doesn't matter. So from this, we can construct the one particle state if you want, and use this to construct the density matrix. But this is the covariant density matrix. It's like, for one vector boson, it's like a 4x4. This is not what I want to deal with, because I want to look at the spin density matrix. So what we do is that we use a projector, which has this shape, and it depends on the spin matrices, and then some spin 2 guys here. And with this projector, we let him project our covariant density matrix on the polarization basis that we are interested in. So the result, after a bit of math, is this. Not surprisingly, but basically you can write it from the amplitude by using this projector once you know also the spin summed square matrix element. So if you do this thing for 2 vector boson, at the end of the day, you will obtain something of this form. Here I picked as a basis to, I mean, this is just 9 by 9. You can write it on the basis of the German matrices, or the tensor product of the German matrices, or spherical tensor, doesn't really matter. One is the other. You will have these parts, which we learned about before. These contain the information about vector and tensor polarization of the singular vector boson involved, and this contains the correlations. So basically, that's it. So we started to compute from the usual diagram, right? One problem is that the Higgs is light enough. The one vector boson is always off shell. So how do we model that? Well, I don't know if off shellness is a word, but now it is. So we just introduced this parameter f for a measure, for like as a measure of the off shellness, and then basically consider the mass of the virtual boson like a mass of the actual real one modified by this f that is more than 1. With that, we compute the amplitude, which has this form. Here is the new bit, which depends on the new couplings. And then you compute the square as before. This is usual, like we do in kindergarten, right? And then you get your density matrix that, as promised, depends on tensor product of 2 of these polarization projectors operator. It has this form. So yeah, for fixed F, it is a pure state, and it remains a pure state regardless of the values of the coupling. Here I wrote, it's very small, so you cannot see if there are typos, but anyway, it's the different expression in terms of the kinematics and stuff like that. So as promised, the pure state looks like this. And yeah, you can compute your density matrix and blah, blah. This is just the same as before. Just to make it a bit clear, this is like if I want to write it in terms of this H and F and G coefficient that you've seen in the expression that I gave before in terms of on the basis of the tensor product of the German matrices. I included this thing just to remind you that, of course, like for instance, like Alan told us, like you can physically reconstruct this thing from measurements and your F, G, and H. You plug it in here, then you plug them in there, and you get your density matrix. So this was the theoretical part, let's say. Now let's move to the point. It's like, okay, all observables are quantum in nature in the sense they're like were made of quantum stuff, right? But three, which are the one that we use, are more than other, let's say, they're a bit different than the usual observable that we test at collider. So for a pure state, we can measure the entanglement through the entropy of entanglement that is given by this expression, where these are the reduced density matrices, no, which you obtain from the big density matrices, but tracing out the vector boson you don't care about. For our choice of normalization, basically for our choice of the logarithm, the entropy will stay in this range. It is 0 when you have a separable state, and logarithm of 3 when the state is maximum entangled. Then, for an arbitrary state, we could quantify entanglement with a concurrence. It has, for a bipartite pure state psi, it has this shape. And then, if for a general mixed state, you have to do your convex roof extension, and you get something like this. The problem is that this thing is very hard to compute, so we don't want to do that. And instead, we've been lazy and used just a lower bound on the concurrence, which is this C2. So this C2 is a witness. It doesn't tell you how much entanglement there is, but it tells you if there is entanglement or not, which I'm fine with it. To me, like good phenomenologist approach is that C2 is just a number. If in the standard model is 1 and I measure it to be 1.5 and 1.5 is 5 sigma away, I get the Nobel. That's it. So yeah, I mean, and then the third observable that we use is something that we build up. There's no name, it's called C odd, it's a bit odd, but it's basically antisymmetric part of the density matrix. And if you look at what it means, it's basically stuff like this on triple product of momentum polarizations. Now, a few remarks. Where we did all the computation at 3 level. So there will be next to leading order correction to F, G, and H, so to the density matrix and to the observable that we use. That will be in order 1%. Okay, who cares? And then as for the sensitivities of this observable on anomalous coupling, the nice thing is that the entropy of entanglement at the lowest order is linear in AV and quadratic in A tilde V, which means that mostly it's going to probe these things. These numbers are expected to be small, meaning that quadratic you can neglect. And C odd instead is linear in E tilde, and at the lowest order depends on this. So also in the case of C odd, the dependence on AV is suppressed. This means that these observables seem kind of ideal for constraining parameters, no? Because the linear dependence of basically of this coupling, of the observable on the coupling, will automatically suppress the cross correlation quadratic and therefore negligible. The strategy we came up with is nothing new, is the usual chi-square test, which we set for 95% of confidence level. And we use on top the observable, which will be taken in pairs between C odd and the entropy, or C odd and C2, depending on the purity. And the only problem was like, what number do I put here? So like, I don't know how to compute. So for understanding, for solving this problem, we took a step back and we look at the processes that we are interested in. And they basically, LHC, they show up like this. Now, if we consider only E and mu final states, because they're cleanest, we get this number of events after selection and blah, 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 blah. In this analysis, the reconstruction of the Higgs rest frame is crucial also to determine the mass, which was the purpose of these things. And coincidentally, the same reconstruction is also the main source of uncertainty in the determination of Z star and WW, just because, like in the way we compute this, you have to boost in a Higgs rest frame where these two things are back to back and so on. So the main idea is that, okay, I can then use the error on MH as a proxy for all the uncertainty in this thing and compute this number by a Monte Carlo simulation, which we obtain now by changing, basically by sampling the Higgs mass in a distribution within the error. Then I get my distribution for the observable. I look at the variance, and then I know what to put here. This thing works well for the Z star because the error is very low. And this is because, again, we restrict to muon and electron final state. But it doesn't work too well for Ws because they have the tendency to decay to neutrinos most of the times. There are some neutrinos, and therefore you get the 5 GeV uncertainty for the reconstruction. In the following, we refer to semi-leptonic decays in which some S jets are identified via the C tagging of the companion jet, and take half of that, because obviously there's only one neutrino. If it is 5 GeV for 2, is 2.5 for 1. Come on, and then use that as an uncertainty to for the distribution of the Higgs that we use to construct the distribution of these things that at the end of the day tells us this number. Anyway, it won't matter because the W doesn't perform well. So results in theory, in a sense that, yeah, in an ideal world where we can ignore the backgrounds, this is what you get. So we do our chi-square test, and these are the anomalous coupling, and these are the 95% confidence limits. Here I marginalize them, meaning that I read this number, this number, this number, and this number, and I report it in the table. And at this point, we wanted to know how well we did. So we found in the literature some bounds that came from the Higgs-Dralum process. So you have a Z that goes in a Z and the Higgs. And they were looking at some polarization observables, but not at entanglement. And they found these limits. Our limits looks pretty competitive. And this is prior to some rescaling due to the fact that their limits are in production and the anomalous coupling is not dimension 4, it's dimension 5, and so on. But basically, I mean, it seems like pretty okay. So for this, we were quite happy. And now there's the more realistic with like 3 things, in a sense that is more realistic in a sense that, yeah, we included the background, but we computed the background. So it's more realistic for a theorist like me. So to do something more realistic, we computed the background. This is like PP to double 2 vector bosons, basically massive vector bosons. We computed that by electroweak interaction. And then we used this value of signal over signal plus background to compute the final density matrix, which will depend from the signal and the background. With this thing, we focus on the Z case only because it's the one that performs the best. We have obtained this 95% confidence limits. Now, the important thing is that inclusion of a background, which, okay, I mean, it's you can tell the background from the signal in this case. Anyway, causes these limits to worsen by a factor of 1.5, which is not too bad. And the tilde limit instead, so the limit on the CP odd coupling is the same as before, just because the background nicely is CP even. So this guy is the same as before, didn't get worse. Now, again, we wanted to compare our finding with something in the literature, and we found a paper by CMS where they were analyzing this anomalous coupling in terms of these quantities, where the sigma 2 sigma 3 are basically the cross section that you obtain by turning on only the second or third coupling as designated in the papers. But basically, these things are related to our observable in this way. The bound that they gave for these things are here, and if I did the computation correctly, we obtained this thing here. So, like, it seems like entanglement in general, and this kind of observable, the density matrix, if you want, is like rather powerful tool for constraining new physics models. Of course, if you want to think about it, it's like, yeah, it is the case because we are using a lot of entries of the density matrix, which means that it's, I'm almost finished. It's basically, of course, it's more sensitive than bounds that only use like a cross section or so. But anyway, I mean, still, it's a good. I would say it's not hopeless at all as a method. So this brings me to the summary, I believe. So quantum tomography, it's provided me to reconstruct the full state, the full quantum state of the system that we're looking at, and we apply this to the study of the polarizations of the massive vector bosons, to understand if anomalous couplings that could be originated by new physics model beyond the standard model or could be constrained with these methods. To do that, we identified 3 observables that provide, in our opinion, the most stringent limits to date. 2 of them are linked to entanglement, which are the concurrence and the entropy, and the other one to the CP test is basically the possible CP nature of the Higgs boson. For the HWW channel, the power of our method is diminished by the presence of neutrinos in the final state that lead to a big uncertainty basically on the reconstruction of the X-ray frame. For the ZZ channel, instead, the results we obtain are very competitive and they are like in line with the best current bounds. So our hope is that this kind of analysis could be included in the routine experimental analysis just to improve our knowledge and to further constrain the physics beyond the standard model. So thank you.
Thank you a lot. Okay, thanks.
I'm a bit surprised when you mentioned that since the background is symmetric, the limit on the tilde coupling is the same. I mean, the precision. Yeah. The same or practically the same?
How I included the background is the same because it's the standard model background. It's CP even. So this part, this tilde coupling, the operator that we use to test the tilde coupling doesn't see CP even.
Yeah, but the point is, imagine you have a background.
Yeah.
And the background is symmetric. You have a distribution which is not symmetric. You will have to subtract the background to extract the coefficient or whatever.
No, symmetric, I mean CP symmetric.
Yeah. Okay, but at the end, even a symmetric background increases the statistical uncertainty on what you want to extract. When you subtract the background, the statistical uncertainty is on the total number of events, signal plus background.
Yeah. But okay, as I said, these are more realistic in the sense that I wanted just to see how much the background changes basically these observables. You're talking about how it scales with statistics.
Not only. I mean, but okay, but we can talk later.
Okay.
Okay.
Thank you for talking. I'm curious, not just a question. Is there a way to use some alternatives of quantum tomography when you have, for example, for the HWW channel, of course, there is the problem of neutrino. Are there any techniques out there to help to reconstruct the density matrix, like classical shadow techniques that is used in other kind of application? Is there any idea?
I'm actually looking into this, so I cannot reply, but yes. Yeah, I have hopes, yeah, I'll say.
Thank you very much for the talk. I have this question about the C2 because it behaves differently in case of pure states and mixed states, as far as I remember. So for pure states, it seems that you can analytically, there is only this optimal form. You can just put some special projector that is asymmetric in the formula and you get it. But
Yeah.
when it is mixed, so when it is mixed, this this formula is for pure state?
I don't remember for which one it is, honestly.
Because when you have mixed state, there is you put some projector that is rank 1
Yeah.
two body for 2x2 antisymmetric.
Yeah.
But of course you may take a lot of them. So basically it is bound depends on the choice. So they have some optimization over I think over parameters. So I'm just curious which one is there. For pure state, it doesn't matter.
If you don't remember, I don't remember for sure.
All right. Thank you.
So my understanding is that formula is for a pure state is exactly the concurrence. For a mixed state is a lower bound.
Yeah.
So my question was, you just take the same projector that pure state or something else?
Yeah, I don't know about, yeah.
Any other question?
Any other question?
People from home? No?
Yeah.
Yeah, I have thanks for the talk. I
You're welcome.
might have two. So first is like, what is the value of F of the off-shallowness? And also maybe it's related, when you project this project in the beginning, does it put the polarization tensor in the mass shell and becoming a
No,
Q-treat?
the projector, it has, I mean, it's on the mass shell, but it's on a mass shell with a fake mass, right? So in the same spirit as we used, as you model an off shell, like an on shell with a different mass. So that's what it does. I lost the projector, it was here. For F, we kept F fixed and then we changed it a bit to see if bounds were changing, but no, that is not super sensitive to the very precise value of F. So we didn't really care.
Okay.
Unless you pick like super extreme cases. Yeah.
So it's still like a Q-treat, but with 4 degrees of freedom, right? Of the Q-treat itself, but also of this off-shallowness.
Yeah. There's always there.
Right.
Yeah.
Okay, thanks.
I have a question. So when you reconstruct the observables you mentioned, do you apply any kinematical cut to the object you use to reconstruct them, or just take
No. Cuts are above my pay grade. So like what we did, what do you mean by reconstructed?
No, because I thought that you were taking a so this is all calculation, right? You're not taking any.
No, this is the best case. Then of course, everything I showed you, it will become much worse when you actually do it.
Yeah, of course. No, but it's like, so basically the early experimental part is the way you calculated the sigma in the formula, right? The taking from mass.
Yeah. Yes.
Every effect is considering in that value. There is nothing.
Yeah. So the main assumption for our calculation of the error is that you can model the error. The main source we know is the X rest frame, and then we took that as a proxy for all the errors.
I forgot to ask before, are there questions on Zoom? No, okay. Thank you again to the speaker. Okay, so now Eric will talk about probing new physics through entanglement in boson production.
Yeah, thanks. So this is work I did together with Rafa, Luca, and Fabio. Yes, so in this workshop so far, we already heard about different channels at colliders that can be used to test entanglement. We heard about top pairs, Higgs decays to weak bosons, and also direct production of weak bosons. And now we also heard about several ways to use this to test new physics, in particular in top pairs yesterday and now today for Higgs decays to weak bosons. And in this talk, I will now complete this by talking about new physics effects in weak boson pair production. This also means that a lot of the things that I would usually say in seminar talks have already been said. So here it will be a lot of plots I'm showing after a short reminder of things you already heard. So let's start with the framework we are going to use. Here we're going to study new physics in the framework of the standard model effective field theory, where we assume that there's some new physics that's some high scale lambda. Above the scale, we have this new degrees of freedom, and below the scale, we can describe this as an effective field theory, where we only have standard model fields. So we take the standard model Lagrangian, add new operators, where these operators here are higher dimensional operators composed of standard model fields only, and respecting the symmetries of the standard model. These Cn here are the so-called Wilson coefficients, and then these higher dimensional operators are suppressed by some power of the new physics scale. In particular, here we are only going to take dimension 6 operators, and here, for brevity, I will absorb the scale dependence of this lambda squared factor in our Wilson coefficients. So I only need to write the lowercase c's when labeling the axis and don't need to write the lambda explicitly every time. So this gives us a kind of model independent way of describing new physics. Now, if we want to add all possible dimension 6 or higher dimension operators up to dimension 6, this can be done in the so-called Warsaw basis, where we have one dimension 5 operator, the Weinberg operator, and then if we only consider flavor universal interactions, we get 59 operators that respect barrier number, and then for extra barrier number violating operators at dimension 6. However, for the process we are considering here, there are only 13 relevant operators if we, in addition, want to respect CP. Again, this is flavor universal at dimension 6. So this is a list of operators we are considering, and here in the third column you see the current bounds on the operators. The scale here is, these are in units of 1/TeV squared from the Smethit collaboration. We here have the operators that modify that couple to the right-handed up and down type quarks. Then we have SU2 singlet and triplet couplings to the left-handed quarks. Here's the same thing for electrons and leptons and the lepton doublet. And then these operators here with triple or 3 W field strength tensors, and then interactions with the Higgs boson. Okay, so let me walk you through the effects of these operators. First of all, some of these operators induce some generic or some universal shifts in the parameters that appear in our interactions. First, these two operators here, this is the triplet coupling to leptons, and this is the 4-lepton or 4-fermion operator. These induce shifts in the Fermi, in G Fermi. Then these two operators here induce a universal shift in the weak mixing angle. And these 3 operators here give us a universal shift in the charge independent coupling to the Z boson. Then these first 4 operators here change the couplings of quarks to the Z boson. These first to the coupling to right-handed up and down quarks, and these two change the coupling to the left-handed quarks. And this operator here also changes the coupling of the left-handed quarks to the W boson. Then here, these couplings or these operators change the electron coupling to the Z boson. Again, here, right-handed electrons and the left-handed lepton doublets. This is singlet and triplet SU2 operator. The triplet operator also induces changes in the couplings to the W boson. The triple gauge couplings are modified by these 2 operators here. And also this one, and this one is special because it induces new Lorentz structures, so coupling between new weak boson polarizations that don't interact in the standard model. And then we have direct modifications of the Higgs couplings. These here modify the couplings of the Higgs to quarks and leptons, and then these here to weak bosons. Now, for what we are going to do, these I will not talk about these operators here. For first of all, this one here only leads to this universal shift, so it cancels out when we normalize the R matrix. And then these two, the only effect was to change the triple gauge couplings. And since in the end, or for most of the calculation, we are setting the lepton and quark masses to 0, these operators will not contribute. But these would be the ones that would contribute to the changes in the Higgs to HWW and HZZ couplings that were tested in the previous 2 talks. Okay, so if we now, in order to see how new physics changes the entanglement patterns, we calculate the first the matrix element, including dimension 6 corrections, and then the R matrix. So the R matrix is just the square of the matrix elements averaged over our initial state degrees of freedom and summed over all the final state degrees of freedom instead of the spins. These are kept as free indices, and then if you're considering a proton collider, we have to weight the different initial state channels with the corresponding luminosity functions. Now, our matrix element in SMEFT has the standard model contribution and then these dimension 6 corrections. So if we square it, we get 2 types of new physics terms. First, we have the standard model part here. Then we have the dimension 6 corrections, which come from the interference of the standard model with the corrections in the matrix element. And then in addition, we can also get these dimension 6 squared contributions. So then we calculate the spin density matrix rho by normalizing this R matrix to the trace. So it's normalized to unit trace. And then we expand in terms of our new physics scale. So here I wrote this still explicitly with the new physics scale. Yeah, and we take into account both the dimension 6 and the dimension 6 squared corrections. And the similar kind of expansion we do when we calculate the concurrence, or to be more precise, the bounds on the concurrence, and then also purity and violation markers. However, here I'm only going to show you plots of the concurrence. So for a system of 2 qubits, the concurrence for a pure state can be calculated by using this expression here, where we take first the partial trace over one of the subsystems of our density matrix, square it, and then take the trace, and then subtract this from 1, multiply it by 2, take the square root. And then if you want to do this for a mixed state, you do this by the convex roof expansions. We already heard about this before. So this gives us a number between 0 and for 2 qubits, this is 2 over square, the upper bound is 2 over square root 3. And the positive value, or the positive value of this means that this is entangled, or this state is entangled. However, for this calculation here cannot be done analytically. So in order to have an analytic estimate, we then go back to upper and lower bounds on the concurrence, which are given by these expressions here. And again, in the following, I'm only going to show you the lower bound. Yes, so you can see here that since for pure states, the trace of the square of the density matrix is 1, in this case, these two expressions coincide, and they also coincide with the pure state expression of the concurrence. Okay, so now we come to the part with all the plots. This is first for W pair production in electron colliders. Here we have the standard model picture first. This is the lower bound on the concurrence. Here we have the scattering angle, and here this is the invariant mass of the W boson pair. So in the standard model, we get something entangled in most of the phase space, and we get quite large amounts of entanglement in the central region and also in the backward region, whereas in the forward region, it's the entanglement is rather low. If we now add new physics contributions, this looks like this for some selected set of operators. This here is for the coupling, for the operator that modifies the coupling of the Z boson to the right-handed electrons. For this choice of sign of the Wilson coefficient, this enhances the entanglement in the central and in the backward region. The second plot here shows the operator that modifies the coupling to left-handed electrons of the Z boson. Yes. So in this case, we get less entanglement in the central and the backward region at high energies. Whereas these lower two operators here modify the triple gauge coupling. In particular, this one is the one that adds the new Lorentz structures. And these have a rather small effect on the concurrence. As you see in all these cases, the forward region kind of remains untouched. So if we now reverse the sign of the Wilson coefficient, we also reverse the effect. Now these here we get a smaller concurrence, and here the bigger concurrence. However, you note that this is not a complete, and this still looks kind of different if you compare these two, which also shows that there's some contribution from the dimension 6 squared effect. So here for comparison, next slide. Here for comparison, you also see the dimension 6 corrections only. So this is only taking into account standard model plus dimension 6, and this is standard model plus dimension 6 plus dimension 6 squared. And yeah, especially at high energies, we can get a sizable effect from the dimension 6 squared corrections. So now another thing we can do is look at specific parts of the phase space. Here we just look at a single point, namely an invariant mass of 500 GeV and the cosine theta of 0. So this is in the high energy central region. Here we have a set of, now we turn on 2 Wilson coefficients at a time. The colored region is the way the lower bound on the concurrence changes. So this is the change in the lower bound divided by the standard model value. And the lines show the change of this A tilde, which was the coefficient of the unit matrix in the Fano decomposition of the R matrix. So this tells us how the differential cross-section changes. And you see that at least in some cases here, we have the nice effect that the way the cross-section changes is almost perpendicular to the way that the concurrence or the lower bound on the concurrence changes. However, for some other operators, this is not the case, like here, for example. And you also see that, especially here where we have this new Lorentz structure that does not interfere with the standard model, at least in the not in the cross section, we have we get these lines are curved, which again tells us that there's an effect from the dimension 6 squared. So you also see this when we add only the dimension 6 without the dimension 6 squared contributions. In this case, of course, everything is straight because we only have linear corrections. So the next channel we're going to look at is proton-induced W pair production. So here on the left, we have what we get if we only look at the up channel. On the right, in the middle, we have only the down initiated channel, and then on the right, we have the full proton collisions where we add the two weighted with the corresponding luminosity functions. So you see here, these have kind of opposite effects. Here we have low entanglements on the left side, high entanglement on the right side. And if we add the two, we have both in the backward and forward direction, low entanglement and then high entanglement in the central region. So this is what we get if we add new physics effects. Again, well, these two add the right-handed quark couplings to the Z boson. Here we get less entanglement for, less entanglement at high energy. This operator here is a triplet operator that modifies the W coupling to left-handed quarks. Here we get more entanglement at high energy, and then here, this is the one that induces the additional Lorentz structures. This also reduces the entanglement at high energy. Now here, if we change the sign of the Wilson coefficient, still the effect is the same. I mean, it looks different, but these operators reduce the entanglement of the concurrence, and this one enhances it. So we see that here again we have large effects from dimension 6 squared operators, dimension 6 squared contributions. Well, here's again the same thing for the specific phase space point. So here this looks less promising because usually in all these cases we have the directions at the cross section and that the lower bound on the concurrence probe are similar. This is again only dimension 6. Now let us come to electron 2ZZ. Yeah, this is the standard model picture. Again, it looks with symmetric, low entanglement at backward and forward region, and then higher entanglement or higher concurrence in the middle. And here, if we add these higher dimensional operators, the effect of both well, the two operators I'm showing here kind of look the same. And the reason here is that is the following. First, these are the two, the three diagrams that we have. And if you know a little bit about the standard model, one of them already looks suspicious to you. First of all, this one we don't have because we set the electron mass to 0, but that's not the suspicious one. The suspicious one is this one, because simply this vertex here does not exist in the standard model and also not at dimension 6. This is due to the SU2 gauge structure. So we only have this diagram, and all our Wilson coefficients can do is change the balance between the left-handed and right-handed initial state contributions. Yeah, so as a result, yeah, we can only change this balance between the two contributions. And this now is proton-proton to ZZ. We have an additional effect because now we have the up and down initial state channels, which we have to sum, which again leads to an additional reduction of our concurrence compared to the platonic channels. And here we only get very small corrections in this region here, in the low energy backward and forward region. So this is not a very promising channel to probe new physics. And the last one channel I'm going to look at is WZ production. If you only have the platonic cross-section, this produces a pure state that looks like this. Now, if we look at proton colliders, we still have to symmetrize this because the D bar can come from either proton, which again gives us a mixed state. However, in this case, we are still sensitive to new physics, in particular to this triple W operator, which induces the new Lorentz structures that do not exist in the standard model. Yeah, so this is my summary. We can modify the standard model entanglement patterns with new physics, which then can help us to probe new physics. These first three channels are sensitive to dimension 6 modifications, whereas the Z channel is less sensitive to dimension 6, but potentially it can be sensitive to dimension 8 operators. Thank you for your attention.
Thank you a lot. Questions?
Very naive one. Can you go back to where you show the concurrence?
Uh,
No,
which one?
yeah, one back maybe.
uh,
Mm.
this one or?
Another one?
Uh,
Yeah, okay, this one. I'm a bit confused. Do you show here concurrence which is larger than 0? Could it be? Right, because you have a part which is larger than 0 and also in the the contour.
larger than 0, yes.
Larger than 1.
Yes, for qubits, the maximal value is not 1. It's what was it, 2 over square root 3 or something like this.
Ah,
I had it
okay.
here on the, yes, 2 over square root 3.
Okay, I see. Okay.
Other questions? Okay, I have one question. So it's not great for proton-proton collision, right? To use this to search for new physics. So the most promising channel for us to study at LHC, what would it be probably?
I think HWW is probably still the most promising one. Or WZ maybe. Yeah, it depends also on the operator you want to look at. But here you can still get some sizable effects even in the region where these. So all these values for the Wilson coefficients are within the current bounds. Yeah, so you could still see the effects in the WW production and probably also WZ.
Are you also trying to study if the limits that we can get with this type of measurements are comparable what we already have in the global fit, like similar to what Claudio showed for TT bar?
We did not look at this. All we did was an analytic calculation, and then to get the limits, since this is beyond cut and count, it's without simulations, it's getting difficult.
Okay, any other questions? No, so thanks to Eric again.